Hello, and in the last for now talk about electromagnetism, I want to have a very brief look at transformers. Transformers are produced when you take two coils of wire and put them in close proximity, so that the magnetic field generated by the current in one coil also goes through the other coil, and therefore any change in this magnetic field caused by a change in current in the first loop will produce a change in the magnetic field in the second loop, and therefore a EMF in that second loop. So we're producing an EMF in the second loop by changing the current in the first loop, despite there being no physical connection between the two, apart from the shared magnetic field. To analyse the behaviour of transformers, you have to take account of the fact that this effect goes in the other direction as well. Any change in current in the second loop will produce an EMF in the first loop. The magnitude of this effect is quantified by this equation here, where M is known as the mutual inductance. It's the ratio of the EMF produced in the second coil to the rate of change of current in the first coil. And transformers are symmetric in the sense that the EMF produced in the first coil due to a change in current in the second coil would have the same value of mutual inductance. Transformers come in two main types, a core form and a toroidal form. In the core form, you have a single core and you wrap two loops of wire around the same core. They're quite easy to make, quite cheap, but they have the disadvantage that the magnetic field tends to leak out from the top of the core and can cause problems with other parts of the surrounding circuitry. More expensive, because they're harder to make, are the toroidal transformers. And these are transformers where the two coils of wire are wound around a toroid, a sort of donut-shaped core. This has the advantage of keeping almost all of the magnetic field within the circular toroid itself, so it has much less effect on any surrounding circuitry. To analyse the circuit behaviour of transformers can get a little tricky, because you have to take into account both the inductances of each side and the mutual inductance from the other side of the transformer. This is the circuit symbol of a transformer. You'll note that this transformer is a 2-to-1 transformer, which implies that there are twice as many turns on this side of the transformer as there are on this side of the transformer. To derive the circuit equations for transformers, we'll first look at this side, known as the primary side of the transformer. This is the side where power is flowing in to the transformer. A current is flowing in, I1, and it's going down through this coil. Well, that, since this is an inductor, is going to produce an electromotive force across this coil, given by E1 equals L, that's L1, the inductance of this primary side here, times the rate of change of the current through that primary side of the transformer. But that's not the only contribution to E1. There's also a contribution due to the changing current that's flowing through the secondary, because this is going to cause a changing magnetic field in the core as well, and therefore a contribution to the EMF on this primary side. So we have this other term in the EMF on the primary side, the mutual inductance times the rate of change of the current on the other side, the secondary side. And we apply exactly the same logic to work out a complete expression for the EMF on the secondary side, E2. It has a contribution from the changing magnetic field caused by the current in the secondary, I2, and also a contribution caused by the changing current on the primary side, I1. We can use these formulas with nodal analysis and solve this circuit. The derivation gets a little tricky, and I'll refer anybody interested to the short introduction documents. The only thing you need to know for this module is what effect an ideal transformer has for a sine wave input. And in that case, the ratio of the two voltages, E1 to E2, is the same as the turns ratio, the ratio of the number of turns on each side of the transformer, in this case 2 to 1. So in this case we have E1 is going to be equal to twice E2, because there are twice as many turns on the primary side as there are on the secondary side. An ideal transformer doesn't extract any energy from the circuit either. So we can look at this in terms of power. Well, the power that's coming into the transformer by I1 going down through this potential E1, power in, if you like, is just I1 times E1, power being current times the equivalent of voltage. And that must be equal to the power that's going out of the secondary side, if this transformer is going to be an ideal component. Well, the power that's coming into the secondary side is I2 times E2, so the power that's going out must be minus I2 times E2. Power leaving the transformer on the secondary side minus I2 E2. Therefore, we have I1 times E1 equals minus I2 E2 in the directions that I've labelled the currents in this diagram. In this case, we have E1 equal to twice E2, so I could write this like this. The E2s would cancel, and we'd notice that the current on the secondary is twice the magnitude of the current in the primary. So the voltage halves as you go across the transformer, but the current doubles. There are some ideal transformers in the simulator, so you can play around with circuits involving them there. We'll have a quick go. Here I've built up what you may just be able to recognise is a potential divider circuit with a transformer halfway along. And you'll see that this potential divider is behaving exactly as if the transformer wasn't there. The current flowing into the primary is the same as the current flowing out of the secondary. The voltage across the primary is the same as the voltage across the secondary. So the power being absorbed by the primary is equal to the power being released by the secondary. And that's because we have a 1-to-1 turns ratio transformer. If I change this to a 2-to-1 transformer, then we would have twice as many coils on the primary as we would on the secondary. We would therefore expect the voltage on the primary to be twice the voltage on the secondary. And we get this. We now have 2.4 volts across the primary with 600 microamps flowing through, but twice that current flowing out for half the voltage flowing out of the secondary. The voltage has gone down by a factor of 2 because the turns ratio is 2-to-1, but to preserve the power, that means the current has had to increase by a factor of 2. If I increase the turns ratio to, for example, 10-to-1, then there's a very small amount of load being taken from the primary. The voltage has only dropped by 30 millivolts across this 1K resistor, but we've got nearly 300 millivolts across a 1K resistor at our output. We've got now 10 times the amount of output current as we are taking from our source. Going the other way has exactly the opposite effect. If I was to remove this 1K resistor at the start, and just connect it directly up to the 3-volt source, I've now achieved 30 volts across my load resistor from a 3-volt source. This is a way you can increase the voltage without requiring a power supply. The price you pay is the decrease in the current. Power must be conserved. I can get a bigger voltage, but only at a smaller current. That's all we have time for about transformers. There'll be a lot more detail about them later on in the course.